Okay, so this next video is going to focus on information and computation. Actually, in reverse order, we're going to start off with the discussion of computation. Um, and this will give you, hopefully, the background to how we were thinking about the mind in the middle of the past century. So we've developed more and more ways of automating complex calculations over millennia, really. And the legacy here, you can go back as early as the abacus. You can go to Leibniz talking about binary, which he actually got from understanding of the Chinese I Ching, so developing the first calculators. Punch card controlled loom, which you might argue is the first bit of software. If you wanted, when we started using computing machines in the 1890 in the United States. So around the turn of the 20th century is when a lot of new inventions take hold, and these begin having more and more of an impact. At the beginning of the 20th century, a computer was a job description. By the end, it was a noun of an object, of a technology. And all of it came in parts to the point where it was very, very technical early on and became commonplace by the end. Key in this is a man named Alan Turing, who was a pioneer in computer science, artificial intelligence, cognitive science. He played a very important role in World War II, arguably part of what helped keep the United Kingdom from succumbing to the German force. He invented a machine to help crack the German military cipher, the Enigma, which had been based on this one particular machine. It was a typewriter where each letter typed a different letter, and the code would reset every day. Turing came up with a way of automatically deducing what the code was every day. So the United States at this exact time had also developed a crack for this code, which we don't talk about, but you should definitely read The Woman Who Smashed Codes. There's the female code breakers that we had in the United States were every bit as capable as Turing and Bletchley Park. But Turing went on to have a very influential role in the development of computers, which is why we talk about his history here. I'll talk about his personal life very briefly. He was a gay man, possibly somewhere in the non-neurotypical spectrum. And after the Second World War, it was discovered that he was gay, and he was given the option of either taking chemical castration, which produces the results sort of like what you see at the bottom left, or going to prison. Seeking to avoid this, he took chemical castration, which are really chemicals to interfere with his hormone production, make him essentially impotent. They also interfered with his ability to think and to do math. So he committed suicide in 1954 by eating a poisoned apple, an apple that he injected with cyanide. People think that he did that to give his mother plausible deniability as a Catholic, so that she would not think that he had killed himself. He worked with cyanide. It was easy to imagine making that kind of mistake. He was eventually forgiven by the Queen, something like 50 years later. So his story is sad, especially because he was a genius, way ahead of his time, and who knows what else he could have done had he been allowed to live beyond the age of 42. He he developed this idea of a machine that could compute, and he had a thesis, which is really a philosophical claim that anything that is effectively calculable are the functions that could be computed by a machine, which is called the Turing machine, which we now call a computer. So I'm going to go a little bit in detail over that so you can kind of understand what that means. Imagine you have a pen and a sheet of paper, and all you can do is make a mark, erase a mark, move to the right, and move to the left. So the sheet of paper, you have to imagine it's an infinitely long sheet of paper, or at least you have an arbitrarily large amount of paper that you can write on. So make a mark, erase a mark, and move to the right or left, or up and down. You can easily imagine, given that simple setup, how you could draw an ink drawing of the Mona Lisa, or how you could write the most elegant proof, how you could draw anything. You could do any number of things with that. That's essentially what a Turing machine is. It's just a much, much more automated approach. So you have to imagine an infinite tape. Here, I told you to imagine a sheet of paper. It's the same thing. So this tape, this paper, you have to be able to read what's going on in it. So you have to be able to detect whether there's a mark on it. In computer terminology, we call these zeros and ones, but in the metaphor of a pen with a sheet of paper, it's just a mark. So you have to be able to read what's on it. You have to have a program that tells you what to do, what operations to run, in what order. That's going to be your general your plan of attack, your strategy. And then there's also a current operation. That is what you're currently doing. That's more of a tactic, right? So you're imagining this infinite sheet of paper. You have to be able to read what's on it. You have to know what you would do if you saw a mark or didn't see a mark. That's the current operation. We'll call that Q1. And you have to have an idea of what you want to eventually write on this sheet of paper. So that's just, that is a Turing machine. That's a computer. So here's a sample program. It has two functions, actually three. Q1, Q2, and Q3, Q3 being stop, okay? So Q1, there's two possibilities. You're either gonna see a mark or not see a mark. In computer language, we'll call it seeing a 0 or seeing a 1. If you see a 0, you move to the right and you switch your current program to Q2. If you see a 1, you change it to a 0 and you stay at Q1, okay? Now, assume that you've seen a 0 and you move to the right and you switch to Q2. Okay, now you're on Q2. You have two possibilities. You're either gonna see a 0 or a 1. If you see a 1, you move to the right and you stay at Q2. If you see a 0, you change it to a 1 and you move to Q3 and you stop. Very simple program, doesn't really do anything, but it's to give you an idea. So I give you these set of marks on this tape. The first one is a 1. You look at Q1, you're like, okay, if it's a 1, you change it to a 0 and you say a 1, okay. So now I saw this 1, I made it a 0, cool. All right, stay at Q1. If you see a 0, you move to the right. Okay, so I saw a 0. So what I need to do is move to the right. Okay, the tape moves to the right, cool. And now we're at Q2 because that's the other part, Q2, okay. So Q2, now I'm looking at a 1. Okay, if I see a 1 on Q2, you move to the right. All right, so I see a 1 on Q2, I'm gonna move to the right. And now there's a 0. Okay, what do I do in Q2 if I see that there's a 0? If you see a 0, you change it to a 1. and then you switch to Q3, which is stop. You switch to Q3, and you're done. That's it. So this is what happens. You're just imagining iteratively changing a tape or just a sheet of paper. So the Turing machine is purely algorithmic. An algorithm you should look up. Algorithms are just systematic approaches to solving problems, right? It's a step-by-step process to solving a problem. Google runs your life via algorithms. Algorithms are all over the world, but these are just, you can come up with an algorithm for directions to your house, or for making a peanut butter and jelly sandwich, or for complex math. So the Turing machine is purely algorithmic. And even though the cells on the tape carry information, they can be manipulated and transformed in a completely mechanical way. That is, there's no mind there. There's nothing intelligent. So you get intelligent behavior without a mind. There's a stored program, so you have to figure out where you get the stored program. But that's a problem maybe for biology or something else. So people started thinking about minds as computers. Again, I've said this before and I'll say it again. We tend to think about the mind in terms of the most complex technology we have around us. The mind as a machine, the mind as a computer in the middle 20th century. All right. We're going to get to some of the fun stuff here, which we'll come back to next week. But there's this famous quote of Alan Turing. He's probably most famous for the Turing test. Right? So he has this idea of, well, I've developed this idea of a machine that can just manipulate symbols. And then you might ask this question, can machines think? Well, he couldn't have come up with a way of answering that question. He thought that that was too meaningless of a question. Nevertheless, he thought that his general approach could eventually get so complex that you might be able to not distinguish in a scenario as a observer between a machine, a Turing machine, a computer, and a real life human. So he devised something he called the imitation game, which was based on something that apparently they did for fun at the time, but now this is where we get the idea. You are a participant who is given a printout of responses, and you have to decide whether a human or a computer produced those. You have 5 minutes to ask whatever you want to ask, and then you have to decide which is which. We'll spend some more time on that later. Okay. So the Turing test helps get people in the mind of thinking about, in the mindset of thinking about the mind as a computer, as a mechanical, algorithmic, implementing information processor. And just historically, you'll see that the early developments in cognitive science are closely bound up with the emergence of artificial intelligence. Okay. So if we're thinking about the mind as a computer, computers process information. All right. But what is information? It makes sense when you're talking in terms of computers and tapes and zeros and ones. Well, how can we make sense of that when we're talking about individual humans and their many everything that they are exposed to and everything that they do? Good luck. All right. I'm not going to get to information in memory this time. Okay. So let's talk about information. Behaviorism couldn't explain things like basic motor plans. Right? So we talked about the example of signatures. All right, well, behaviorism was talking in terms of behaviors, but if we want to allow ourselves to think about the mind, we have to think about how plans can be in the mind in some way. how they can have some processing. How can we execute them? Enter Claude Shannon. Shannon was interested in information theory and interested in how to understand it. He writes this paper in the 50s, The Mathematical Theory of Communication, where he approaches this question of how much information content do messages have? So like, let's say I gave you two messages, BCA, blah, 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 or ADDA, blah, 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 okay? The question of how much information they have is a tricky one to answer. So we might replace it with another question that's easy, more tractable. Imagine a machine produced both of these messages. And you have to consider whether they were produced by a machine that produced A, B, C, and D, with a 25% likelihood each time, or one that spent more time producing A and about half the time, and then half the remaining time produced D. Right, so this is super abstract. Try to follow if you can. The big takeaway here is that there is a mathematical way of thinking about information. So this is a big question. You're like, okay, Shannon says, how ought we to think about these machines? Which machine is producing more information? So one way of approaching this is thinking about it as a decision tree. Suppose you're playing Guess Who, and you want to divide up the possibilities. Now, you can only ask yes or no questions. So the first question you ask, is it A or B? If you get a yes, you can ask, is it A? And then if they say yes, then you know that that particular spot of that machine produced an A at that instant. If you get a no then you know it's a B. No yes is C, no is D. All right, so with two questions, you can get to calculating exactly what the machine produced in every single spot. Now let's look at machine 2. Half the time it's A. So you should probably ask A for, is it A first, right? You imagine playing Guess Who, and half the people are wearing glasses or something. You say, do they wear glasses? Cool, half the time they do. You don't start off asking the question, are they a bald redheaded person? Because you're gonna be really, really lucky that one time, but most of the time you've just wasted your first question. So is it A? If yes, then you know it's A. You get it in one question. Is it D? If yes, you get it in 2 questions. Is it B? If yes, you get it in 3 questions. If no, you get it in 3 questions. So at least in machine 2, about half the time it takes you 1 question, a quarter of the time it takes you 2 questions, and a quarter of the time it takes you 3 questions to get to what the results are. If you do the math, it turns out that machine 1 you have to, well, you don't have to. You can imagine asking, is it A, is it B, is it C, is it D? And 25% of the time it's taking 1 question, 25% of the time it's taking 4 questions. The most efficient way would be at least 2 questions per symbol to decide whether the machine produced a particular marking. With machine 2, if you just do the math, you calculate that actually it's about 1.75 questions per symbol on average. So there is more surprise in this first machine, right? So if we translate the term information, as Shannon urges us to do, as a measure of how surprising outcomes are, then a machine produces less information if there is less surprise about its output, right? It takes fewer questions to find out what symbol is next. If the machine only ever produces A, then there is less information than a machine that is producing random results. One of the weird consequences here is that a completely random sequence contains more information than one that you could compact in some way. So if you memorize 29 unique names, that's more difficult than memorizing 12 names that all repeat up to 29 times. That sort of makes sense? So I'll repeat this. Memorizing lots of numbers is harder, that is, it's more information, than memorizing fewer numbers. So if you can come up with a cool mnemonic to shorten something you have to memorize, you've compacted how much information is there. You can have a very precise mathematical way of framing how surprising an environment is. In the case with the machines, we were talking about machines producing outcomes. We could tell which one produced the most surprising outcomes based on how many questions you had to ask to figure out what the outcome was. A completely random machine would produce the most information. That is, it would be really, really hard to memorize it. So that's information. Transmission for Shannon is going to be is going to involve a lot of noise and a lot of coding and decoding. So a source speaker, let's say, tries to send a message. They send a signal. There's going to be some noise. The receiver receives a signal plus the noise, and they have to decode the message. So Shannon information here, you're not actually worried about what's in the message, the properties of the message. Instead, you're worried about the formal aspects, syntax, not semantics, if that helps you. If it doesn't, don't forget I said that. So Shannon's a cool way of helping decode how information is transmitted. And that means that you can approach how organisms, how humans respond to their environment without worrying about what's going on in their mind. You can actually just measure the formal properties of what they can recall. You can quantify what humans can recall from their environment. All right. Early cognitive science explored the idea of channel capacity and began asking this question about, like, how many bits of information in Shannon's terms can humans recall? And there is this magical number 7 plus or minus 2. And so to understand this, it was basically, if I give you a list of numbers, you start, you can remember 2 numbers. I tell you 7 or 2, you remember those very easily. If I tell you 30 numbers, you forget most of them most of the time. So even though you could distinguish, like if I give you a list of 30 numbers, and then I gave you a different list of 30 numbers, you might be more likely to distinguish that they were different if you looked at them. You might not recall them, whereas with 7 numbers, I can give you 7 numbers, and you can more or less recall them. Some people can recall it's 5, some 9. So phone numbers are 7 digits. So you can have apps, you can judge stimuli and calculate how much information is in various stimuli and calculate the differences between them. And it turns out that with early cognitive science, we thought that we could quantify all of the sensory modes, that is vision, sound, everything. And there was like a built-in bottleneck where we could figure that out. This, we could recall about 7, so I said that before. Now you can actually improve beyond recalling 7 random bits of data if you do a bunch of tricks. So you can recall different aspects, right? You can recall more than 7 things if you recall not just what they are, but where you were, where they were, what they looked like, what font they were in, that kind of stuff. You can chunk groups, so you can decide that 1, 2, 3 is a thing that you just recall very quickly and easily. And so now whenever you see 1, 2, 3, you can encode it as a single bit of information. You can do all sorts of tricks, but the basic idea in early cognitive science was that it was possible to calculate how we recalled, how humans in general, right? So we could finally get inside the mind, so to speak, in a purely mechanistic way, without appealing to people's inner thoughts and without doing something as crude as just looking at their behavior. And so we're gonna, later on in the semester, we're gonna talk about some of these information processing models. How humans are able to pay attention to certain things when certain stimulus catches their interest, right? So if somebody says your name at a cocktail party, you will start paying attention even if you didn't realize that you were listening. It's harder to shadow messages. There's some physical information, like you can pay attention to whether somebody's speaking to you with an accent and recall that more easily than you can remember what they said. And we basically came up with lots of different ways of breaking up information and exploring how we can process the world, which didn't require appealing to individual to self-reports the way early mentalist approaches did. Okay. So we developed really cool models for how information processing works. And let me just say that these early models were very, very influential. Thomas Kuhn says that a science proceeds by exemplars, that is, these examples of what we call good science. And so these early studies that used Shannon information theory and thought about the mind as a computer, these were so successful that future scientists began appealing to this way of thinking about the world. Okay. So information computation, moving beyond behaviorism, and actually applying some of these to cognitive, to an understanding of the mind. All right, we've done these, and we're moving on to this for the next class period. Cheers.